In this video, we're going to continue to learn about energy, and in particular, we're going to define potential energy. Once we've figured out this new thing called potential energy, we'll see that it's going to modify the work-energy principle and make it much more useful for problem solving. Let's start with a question. We have two water slides, and on one water slide we have Laurel, and on the other water slide we have Jim. The question is, who's moving faster when they reach the ground? Jim has a larger mass than Laurel, and they both start from the same height. They're both on water slides, so friction is negligible. Go ahead and pause the video, think about this, and come up with what you think is the correct answer. Okay, well, it turns out that they will be moving at the same speed when they reach the bottom. So when Laurel gets to the bottom of her slide and when Jim gets to the bottom of his slide, they will have the same speed. Now, you'll notice that the shape of those slides is different. You'll also notice that Jim has a greater mass than Laurel, but it turns out that neither of those things matter. This is going to be much easier to see and understand once we understand the concept of potential energy. Just to add another person to the mix, if we took John, that's me, and let's say we just drop me. I'll give myself a little bit of water here to land in. How would my speed at the bottom compare? Well, it turns out that my speed, when I've fallen through the same height as Laurel and Jim have gone through, my speed at the bottom is also going to be the same. And so once we understand the concept of potential energy, we should be able to understand all of that. In order to understand the concept of potential energy, the first thing we have to do is talk about conservative and non-conservative forces. I know it sounds like we're talking about politics here, but we're not. A conservative force is the following. The work done by a force on an object moving from one point to another depends only on the initial and final positions and is independent of a particular path taken. So this is a hard concept the first time you learn it, to really understand what is a conservative force versus what is a non-conservative force. In order to help us through this, I want to look at two forces that we already know about. Let's start by looking at the force of friction. Now, if friction is a conservative force, what it means is the work done by that force doesn't depend on the path taken. So let's look at an example and see if we can figure this out. Here's a top view of our classroom. And here we have a heavy box sitting on the floor in our classroom. If I asked you to move that box from that position to this position, would you just push it across the floor like that, or would you push it all the way around the room like that? And depending on which of those paths you chose, would the work that you would have to do pushing that box be the same? Well, we all know that when you're pushing a heavy box on the floor, you want to take the shortest path possible. But why is that? It's because friction is a non-conservative force. In other words, with friction, the path matters. If we push the box straight like this, then the work done by friction is clearly going to be less than if we first push it over to this corner of the room, then this corner of the room, then this corner of the room, because we're covering a much greater distance. So friction is an example of a non-conservative force. Let's look at gravity and see if gravity is a conservative or a non-conservative force. Now, to look at the case of gravity, what I'm going to do is I'm going to take this block, and now, by the way, this is the normal, up is the normal up direction. What I want to do is I want to calculate how much work it is to take this box and first move it over to here and then bring it up to here versus just directly moving it from point 1 to point 3. Now, if the work done by gravity is the same over those two different paths, whether I go this way or whether I go this way, then gravity would be a conservative force. In order to figure this out, we're just going to calculate it. So, the first thing that I want to do is I want to figure out the work done by gravity as I go from position 1 to position 2. So let's think about what the work is. We know in general that work is F delta R cosine theta. And let's think about what the direction of gravity is. Well, we know gravity is always straight down, so there's the force of gravity, mg. And if I'm moving the object from position 1 to position 2, that would be delta R. So you'll notice that the work done by gravity in going from position 1 to position 2 is just the magnitude of the force times the magnitude of the displacement, I'm just going to call that L2, times the cosine of 90 degrees. But what's the cosine of 90 degrees? 0. Now, by the way, that makes sense. The force of gravity does not give energy or take energy away when you move something horizontally. Now let's calculate the work in going from position 2 to position 3. So now we're going to go from here, take our box, and see how much work gravity does as we move it up to here. So again, work is the magnitude of the force, mg, the magnitude of the displacement, that's L1. What is the angle between mg and our displacement? Well, notice that our displacement is up from 2 to position 3, but the force of gravity is down. And so the angle between the displacement and the force is 180 degrees. And so what I get is that the work to go from position 2 to position 3 is minus mgL1. Therefore, the total work done by gravity as I go from position 1 to position 2 to position 3 was negative mgL1. Now what we want to do is calculate how much work does gravity do if instead I take this block and I move it directly to position 3. So we're going to calculate the work done by gravity in going directly from position 1 to position 3. Again, we know that work is the magnitude of the force, which is mg, times the magnitude of the displacement. So here's our displacement, so it has a magnitude L3, times the cosine of the angle between them. So what is the angle between our displacement and mg? You'll notice that it's this whole angle, and that would be 90 plus theta. Remember here, our goal is simply to figure out, is the work done in going from position 1 to position 2 to position 3 the same as the work done in going from position 1 directly to position 3? So the question is, did we get the same thing? Now, at first, it's not obvious whether we did or not. We need to do a couple things here. First of all, you need to remember that whenever we have something like cosine of 90 plus theta, we can probably rewrite that in terms of a sine. If you look it up, you'll find that the cosine of 90 plus theta is equal to negative sine theta. So I'm going to rewrite this, that the work is equal to mg times L3 times negative sine theta. But now I want to use trigonometry. What is L3 sine theta? Well, if we look at the triangle, you'll notice that sine theta is equal to the opposite L1 over the adjacent L3. So L3 sine theta is L1. And therefore, I can rewrite this as negative mg L1. And so the work done by gravity, whether this block was moved over our first path or over our second path, was the same. And therefore, we conclude that gravity is a conservative force. You'll notice that we've learned something else about gravity that we probably knew before if we had really thought about it, and that is horizontal displacements for gravity result in no work being done. The only thing that's important for gravity is the change in height. So you'll notice even when we calculated how much work was done by gravity as we went directly from position 1 to position 3, what did we end up with for our answer? We found for our answer that the work done by gravity only depended on the change in height, L1. So that's really important. Not only does it not depend on the particular path, but it's only changes in height that matter. So why do we care about this stuff about a conservative force versus a non-conservative force? Remember that in a previous video, we had determined our expression for the work done by a force, and then we had put that together and developed the work-energy principle, where we said if you add up the work done by all forces present, it's equal to the change in kinetic energy. The problem was that it really didn't help us that much, because if we have something like this, where we've got a block sliding down that curved incline, it's still hard to calculate the net work, because the work done by gravity is not easy to calculate, because the direction or the displacement is still constantly changing, and so this angle is constantly changing. But think about what we just learned. What we learned is that the only thing that really matters when we're trying to calculate the work done by gravity is the initial height and the final height, and that's it. So, because the work done by conservative forces, like gravity, depends only on the initial and final position of the object, we can define potential energy associated with this force, and this is going to simplify problem solving. So again, the only conservative force we know about right now is gravity. And let me just draw out some pictures to make sure you understand the significance of this. Whether we've got a block sliding down a curved incline, like that, or whether we take that same block and simply drop it, or whether that block goes on some complicated looking path, as long as the starting height and the final height of these blocks is the same, the work done by gravity is the same. So that's what we've learned, that we really don't have to do some complicated calculation to find the work done by gravity in those situations. All we need to know is the initial height and the final height. So in terms of what we do with that information, what we actually do is we define something new called potential energy. And the potential energy of an object is simply associated with the position or configuration of the object. So let's see how that works. Before we look in detail at the math of it, I want to make sure that you understand kind of three different ways that we could look at the simple idea of what happens when you drop a ball. So I take a ball of mass m and I drop it. And you could ask, what happens? Well, we know what happens. The ball starts to fall. But why does it fall? Well, if we think about the way we looked at this earlier in the course, we'd say the reason the ball falls is because there is a net force on it, which is the force of gravity. And because there's a net force on it, there is an acceleration, right? So in the acceleration in the y direction would be the force, which is negative mg over m, and we get an acceleration of negative g. So our first way of looking at why does the ball fall is to say there's a net force acting on the ball that causes the ball to accelerate in the negative direction. Now let's take a look at how the work-energy theorem in our current form, W net equals delta K, would explain why the ball falls. What we would say is there is a force of gravity acting down on the object, and the reason the ball falls is because gravity does work on the object as it falls through a displacement delta r. So as gravity does work, mg delta r cosine theta, we gain kinetic energy. So that would be the second way to look at it. The new way, and the way that we're going to be looking at this from this point on, is that instead of calculating the work done by gravity, we define a new quantity called potential energy. And what we say is the object starts out with potential energy. And as that object falls, the reason that it's speeding up is that it loses potential energy and gains kinetic energy. So instead of thinking about gravity as doing work on the object, we define a new quantity, gravitational potential energy, and say the object has that when it's here and it's losing that, and that's what's being transformed into kinetic energy down here. Okay, in order to implement this new way of looking at things, we've got to figure out what the correct mathematical expression is for potential energy. So what I want to do is first figure out how much work would gravity do as an object falls from position y1 to position y2. Well, we know that gravity is in the downward direction. We want delta r to also be down. Our object is going to end up down here at y2. And we now can just go ahead and calculate this. So we've got the force of gravity. We've got delta r. And by the way, delta r, I'm going to put in y1 minus y2. You might think, well, why aren't I putting in y2 minus y1? The reason is, remember that these are magnitudes. And so I need the positive value, which would be y1 minus y2. And then mg and delta r are in the same direction, so I'd have the cosine of 0. What I end up with is that the work done by gravity is mg y1 minus y2. So here's what we want to do. Instead of saying that gravity does work on the object and that's why it speeds up towards the ground, instead we want to say it loses potential energy. So here's how we're going to define the change in potential energy. We use the letter U to represent potential energy, and delta U is going to be equal to minus the work done by gravity. So again, instead of saying gravity does positive work on the object, we want to be able to say the object loses potential energy, and that's why we need the negative sign in that definition. Therefore, delta U is equal to negative mg y1 minus y2. And if I distribute that minus sign, we see that delta U is equal to mg y2 minus mg y1. And if we think about it, what we've really just done is we've defined gravitational potential energy as mgy. So the change in gravitational potential energy is simply the final value of the potential energy minus the initial. Okay, so let's bring this all together. Before we introduce the concept of potential energy, our work energy principle said the change in kinetic energy is due to the work done by all of the forces acting on the object, the net work. What we now want to do is we want to separate out the work done by gravity. So instead of directly calculating the work done by gravity, we want to replace that with the concept of potential energy. But first, let me separate out the work done by gravity, and then I'm going to say plus WNC. So what does WNC represent? NC stands for non-conservative. So forces that are non-conservative are forces such as friction and also applied forces. In those cases, you do have to directly calculate the work done by those forces. But in the case of gravity, we've learned that we can replace gravity with negative delta U. And so what we end up with is a new version of the work energy principle. So now we only directly calculate the work done by non-conservative forces. We no longer calculate the work done by gravity because we've replaced that with a concept of change in potential energy. We'll also talk about the force that a spring exerts is also conservative, but for right now, just think of delta U being related to gravitational potential energy, where U is mgy, and delta K is the change in kinetic energy, where K is 1/2 mv squared. This formula is where you want to start every conservation of energy problem. Start every cons of E prob here. Okay, so just like when we did Newton's law problems, we always first wrote down Newton's second law. When you're doing a conservation of energy problem, start with that. That's where you always start. And you'll notice that every problem we do for the rest of the videos where we're talking about energy, I'm always going to write that down first. I'm going to put a bunch of stars on this slide because that's super important. So let's go ahead and see if we can apply this new idea of conservation of energy, the new version of the work energy principle. And remember, the work energy principle is just stating conservation of energy. Okay, here's the question. Which will be moving faster when it reaches the ground? No friction present. Well, I've already revealed the answer to you, that whether I let a block slide down a steep incline, a more shallow incline, or I just drop the box, these boxes are all going to be going at the same speed when they get down to the ground. So the question is, how would we show that with the work energy principle, with the idea of conservation of energy? Well, what we would do is we would first write down delta K plus delta U equals WNC. So we're always starting at the work energy theorem or work energy principle. And now, because there's no friction present and there are no applied forces, the work done by non-conservative forces is 0. So what does that tell me? It tells me that the kinetic energy gained is just equal to the potential energy lost. But what is the potential energy lost? Well, the final potential energy is just mgy, and the initial potential energy is just mgy naught. Notice that for all three blocks, they both end at the same height and they start at the same height. And therefore, they all will experience the same change in kinetic energy. And therefore, they all have to be going at the same speed when they get to the bottom. Let's go back to our problem of Jim and Laurel and actually solve for their final velocity. So if you remember, we had Laurel over here on this slide, we had Jim over here on this slide, and we'll even look at taking John and just letting him fall. So what is the speed that each of these people are going when they get to the bottom? That's what we want to figure out. Okay, so what do? We always start with the work energy theorem. Delta K plus delta U equals WNC. The next thing we always want to do is look and see, is there any friction present in the problem, or are there any applied forces? In this case, there aren't. Therefore, the work done by non-conservative forces is 0. The next thing we want to do, if we're actually trying to solve the problem, is now write out what we mean by delta K and what we mean by delta U. Remember, delta K just means the final kinetic energy, 1/2 mv squared, minus the initial kinetic energy, 1/2 mv naught squared, plus delta U. So delta U is the final potential energy, mgy, minus the initial potential energy, mgy naught, and that's got to be equal to 0. The next thing we want to do when we're solving problems like this is see if we can cancel out any of those terms. Well, I'm going to define the bottom to be my y equals 0. And therefore, you'll notice that the final potential energy is equal to 0. The other thing in this problem is that all of our people start with an initial velocity of 0. So there is no initial kinetic energy. And therefore, what I end up with is that 1/2 mv squared is equal to mgy naught. Now, it's always good to pause when you get to this part of the problem and see that this makes sense. Remember that the work energy principle is just a statement of conservation of energy. So really all we're saying here is that all three of our people start with this amount of potential energy. Therefore, since all of that is being converted into kinetic energy, they have to end up with that amount of kinetic energy. You'll also notice that here we see that the mass doesn't matter because mass cancels out. And what we find is that they will all be moving with a speed of the square root of 2gy naught. Now, by the way, you'll notice I don't put a plus or minus there because we're not implying that we know anything about the direction. Remember, energy is a scalar. And that means that in an energy problem, we don't learn anything about direction. And so really, what we mean by v here is it's just the speed. So John at the end is going straight down. Both Jim and Laurel are going horizontally. Notice how powerful conservation of energy is. We're now able to see that we can find the final velocity of these objects, and all we had to know was that initial height and the final height. And we didn't have to know anything about the details of the path that was followed. In our next video, we'll continue to look at more examples.